Okay, so hi everyone. Yeah, so I'm really excited to be here. So thanks Marco for introducing a bit of what Topos Institute is, and yeah, I'm really excited to have the opportunity to partner with all the wonderful folks here, hopefully in the coming years. I don't know. It was going so smoothly. Let's see. Okay, so I'll try not to jiggle it too much if I can.
Not to touch it. Try to comment it with the thought.
Okay.
I read that in a morning on the newspaper that Elon Musk made the first implementation of a chip in that will be able to command the computer with the thought. So we should have begun here, possibly.
Right. If only we had Neuralink. Okay.
Okay.
So yeah, to understand where I'm coming from, maybe a little bit about me. So I'm neither a philosopher nor a working scientist. I'm an applied mathematician, and I see myself as a tool builder, a builder of mathematical and software tools. Okay, I'll try to just jiggle it a lot. But I've benefited a lot from reading philosophy of science over the years. Yeah, I suppose could.
Perhaps it seems like because the battery is, so if you could you plug it, or it's just too difficult? You see what I mean? I think it's just a question. You can put it not
Yeah.
in for a few seconds.
So do you want to try another one?
Or can do that. But if you do something constantly, it's
Okay. So right. So I'm going to talk about how I hope ideas from categorical logic can be used to improve the ongoing project to try to formalize theories and models as they are used in science. And in view of the previous talk, which I liked a lot, maybe I want to make a few comments about the general sort of viewpoint that I'm taking here. So I don't believe that there's any necessary connection between a reductionist viewpoint or the idea that all of science should be reducible to some sort of fundamental theory and the idea that there can be value in trying to bring a greater degree of formality and precision to theories and models as they're used in science. And on the contrary, the viewpoint that I'm going to present here is not about trying to reduce everything to a single theory. It's about trying to capture different kinds of models as they appear in their diversity throughout the sciences. And I think that the techniques of category theory bring tools that will help in doing that. So I'm going to start with this quote, which is often repeated because it's rather striking. This is from Patrick Supps. He says, "I claim that the concept of model, in the sense of Tarski, may be used without distortion and as a fundamental concept in all of the scientific disciplines. In this sense, I would assert that the meaning of the concept of model is the same in mathematics and the empirical sciences." So it's quite a claim. I mean, but it's sort of a point of departure for this talk, and a lot of this work is about trying to think about the ways in which models as they appear in logic and categorical logic can be fruitfully connected to models as they appear in the sciences.
I don't know. It's something that I cannot understand. We asked to the technician to comment here, but it is certainly not something that he was expecting.
Yeah.
With Elisa, we tried to take attention to any aspect of the conference, but this was we took for granted that it would have worked.
Because expect that you stay there.
I think that is a problem with the cable, so we
I-
asked for a new cable.
Yeah, maybe a problem with the cable. Um, so I want to start by just setting the stage a little bit about models in the different senses in which the word is used. And probably most of you through some encounter with logic have seen something like what's on this slide, but maybe just to as a place to start, the concepts of theory and model are very well established in logic. They have a precise meaning, and there are a variety of different formalisms that people use. But a fairly typical arrangement is like the one which will hopefully reappear on the screen, where you have a notion of theory, which is a syntactical object, and it might include the specification of things like types and terms and predicates, and then formulas built out of those and entailments between them. And so the idea in logic, conventionally at least, is that that's all sort of happening in a formal language. And then a model is something that assigns to those bits of symbols a mathematical content, like you would assign types to be sets and the terms to be functions, and the predicates become relations. And then if you want to have a model of your theory, all of your entailments need to turn into containments of the relations in your model. So that's a well-known sort of story. So in here.
I just logged into Zoom and I can see it on my screen.
Yeah, so
at least
it's sharing on
see your
Zoom.
slides.
If you want to connect on your laptop and watch, that's definitely viable. So
In any case, next time we will organize a conference on the impact of philosophy on technology.
So the usage of models in science is much murkier. Scientists talk about models all the time, but sort of, often it's just kind of like one when you see one sort of thing. And there are at least two common senses in which the word model, I think, is used in science. So there's sort of the idea of a mathematical model, and like a differential equation or dynamical system or something of that nature that is perceived as relevant to science and analyzed by scientists. And often these models are taken to somehow be more specialized or maybe less universal in some sense than a theory is supposed to be. Maybe even they're disposable in some sense. And this usage of model certainly includes things that don't necessarily have any instantiation in the world. So physicists like to talk about something being unphysical. Well, you could still study it as a model because it might shed some light on a larger theory in an interesting way. And then there's the idea that a model is some kind of representation in an idealized or abstracted form of something that exists in the world. These could be physical models. They could also be mathematical models. So certainly these two uses are not mutually exclusive, and often they're intended to go together. So in this talk, I'm not going to really focus on the representational aspects of models. I'm not going to be talking about the very thorny problems that arise when you try to articulate in any clear way how content in your mathematical model becomes connected to the world. I'm going to focus just on the models as mathematical entities. There's already a whole lot of interesting things to be thinking about, even in that restrictive sense. So just to give some indication of what a scientific theory might look like in some semi-formalized sort of style, this example is often used from classical mechanics in Um, what happened to the spare cable? The spare HDMI cable.
Yes, you stay for 30 seconds and then you disappear. I don't know what is happening in the system, but something happened in the system.
Let me get more cables in. So this is an example that philosophers often use actually, because I think because it's a simple theory, but one that one can like reasonably sort of axiomatize. It's also sort of interesting historically in that it's one of the last examples of a major of a scientist in like a major significant work working in like a formal axiomatic style system. This is a tradition that more or less ended with Newton. So and actually in this talk, I'm going to be focusing a lot on other kinds of models of a more pedestrian kind. Like so my PhD is actually in statistics. That'll be the main examples that I'll be talking about will be drawn from statistical modeling. So I want to emphasize that again that this is not a project about trying to identify, say, the most fundamental theories, but about trying to capture all sorts of different kinds of models. So since this is a conference about philosophy and science and their interactions, maybe it's worth before we get into the details to pause and ask a little bit about what the point of this is. What are we trying to accomplish, or at least what am I interested in accomplishing through this line of work? And so I think that for philosophers of science, there's a quite clear answer as to why you would want to think about theories and models, namely that they're continuously invoked by scientists, especially models. Scientists are always talking about models. And therefore, if you want to have any sort of satisfactory account of how science works, you need to be able to say something about models and how they're used. For scientists, it's maybe a more interesting question. It seems to me that the words theory and model as they're used in science are basically sort of pre-theoretical. As I said before, they're sort of like, when you see them kind of things. In practice, models are communicated in, sort of informal mathematics and just regular text, like in papers. More recently in science, there's been a push, motivated by concerns about reproducibility to publish code associated with models. The idea being that that's at least a more, in some ways, a more precise description of what's going on in the model. And so, I mean, it seems to me that science is in a process of recognizing that there are real problems about the scalability and reliability of scientific communication and trying to make it more precise. Code is also quite imperfect as a medium. It tends to include all sorts of irrelevant implementation details that mix up the description of the model as a mathematical entity with the algorithms that are used to do inference in it. And so for me, this project is really about what can we do to try to make science more legible and to create more coherency between the different sorts of models that people are using. And the hope would be that this is like a mutually reinforcing sort of process where, for the scientists, one would hope that a better philosophical and mathematical understanding of models ultimately leads to better tools and methodology. And for philosophers, the more clarity that scientists have about models and the better their tools are, the smaller a gap there has to be between the so-called rational reconstructions and what scientists are trying to do in practice. And, you know, I think in this way, I very much agree with the previous speaker. I mean, for me, in order to create a virtuous circle like this, it is absolutely not sufficient to argue that formalization is possible in principle. It needs to actually be doable in practice, and best of all, it needs to, if it's really a viable, if it's really useful, it's something that scientists would even consider doing themselves. Which sounds kind of crazy, but I don't think it necessarily has to be if the right tools are available. So for me, this is a talk that's inspired by my reading of philosophy of science, but it's really ultimately aimed at producing tools and methodology. Okay, so in this first part of the talk, I'm going to outline some of the philosophical accounts that have been given of scientific and theories and models, mainly so that I can kind of explain, you know, how ideas from categorical logic might help solve some of the problems that one encounters in these approaches. So for the philosophers in the room, I'm sorry if I'm giving a somewhat oversimplified account of some of these approaches. There's definitely a very rich literature here, and I'm just going to be sort of summarizing some of the major things that people have thought about. So the historically sort of first set of approaches related to logic and science are sometimes called linguistic views, because they're unified by the idea that a scientific theory is, or at least should be, or somehow can be reconstructed as a linguistic or syntactical object that's specified within a formal logical system. So, you know, the best known of these is sometimes called the received view. It comes from the logical positivists or the logical empiricists, who seem to be philosophers of science, sort of favorite punching bag. But there's interesting things, I think, in this work. So, you know, so just to put a little more flesh on one way in which one could try to cash out a linguistic type view, in the view proposed by the positivists, a scientific theory would consist of, first of all, the choice of some sort of logical system. So it's often assumed to be first order logic, but it doesn't have to be. It could be higher order logic. These days, maybe it could be type theory. It could be any system. And then within that logic, the sort of hallmark of this view is trying to distinguish in a definite way between the terms that are theoretical and the ones that are sort of in some sense supposed to be directly observable. And then there's supposed to be some sort of correspondence rules which provide at least some degree of connection between the theoretical and observable terms. And then finally, there's like an intended interpretation, which is sort of extra logical, that is supposed to be attached to this, saying, how would you actually perform measurements, you know, to ground the observation terms. But as I said before, I'm not going to be focusing on sort of the representational aspects of modeling here. So there are a number of problems that this has encountered, and I'm going to focus on, sort of in the spirit of this talk, I'm going to focus on what I see on sort of the practical problems. So first of all, the idea of what's sometimes been called standard formalization. So the idea of formalizing your theory in first order logic, maybe also with set theory added onto it, is extremely cumbersome for essentially any scientific theory, even if it is possible in principle. And I want to emphasize here that this is not a problem about the logic being expressive enough. It's not that, oh, you know, maybe if we just had a better, you know, a richer logic, it would be easier. The point is that there's a big gap between the primitive concepts available, the basic concepts available within the logical formalism, and the concepts that scientists work with every day that are meaningful to them. And so there's just this huge encoding exercise that has to happen there. And then on top of that, you know, many scientific theories and models require significant amounts of background mathematics, things like real analysis, probability, differential equations, all sorts of stuff. And so in principle, you would need to have all that stuff available as well. And then finally, viewing theories in a very syntactical way makes them it's a fairly restrictive way of working with them that makes them hard to reason about mathematically. And it creates mysteries about, what is a theory really? Does it have to be, is the identity of the theory in its precise linguistic expression, or would a similar theory, should it be considered in some sense the same or equivalent? It makes it quite hard to think about these sorts of issues. So so getting back to Patrick Supps, who I quoted at the beginning, and by the way, he appeared on the list of philosophers who published more, I think, in science journals than in philosophy ones in the first talk. So I don't think it's a coincidence that he made a big impact in this area and changed the way a lot of people think, because he was himself he was a scientist himself. He had a lab at Stanford where he worked for many years. And he took a very, a sort of pragmatic attitude to this stuff and wanted to actually be able to axiomatize theories that were of interest to him. And so the approach that he proposed, which belongs to a family of what are now sometimes called like model theoretic views, because they emphasize the role of model much more than the positivists did. So his slogan was that to axiomatize a theory is to define a set theoretical predicate. Another oft-quoted line, because it's a little punchy. The basic idea of his approach, and one that was carried on by a number of other people, is that you specify a theory in some sense by describing its class of models, and for Supps, with the mathematics of his day, the most natural thing to do was to do so using set theoretical methods. And so as I was saying, one of the nice features I think of this approach is that, like, by working sort of semi-formal or basically naive set theory, and availing oneself of a whole bunch of background mathematics that you take to be present there, you can at least, axiomatize theories. And Supps has a book where he does all sorts of ones, including some of the stuff from his own research based on theories of learning. That is to say, how humans and animals learn, not like machine learning mostly. So the essential feature of these model theoretic views is to identify a theory with a class of models. There was a lot of debate about whether theories are not, to the extent to which theories are non-linguistic in this view. Some people explicitly said that they were not supposed to be linguistic entities at all. The sort of viewpoint here is that, one has a model of your system, and then also some sort of model of the data generating process, or some sort of empirical reduction of the theory that's closer to observation, and then you would connect the higher level model to the data via some kind of embedding of the empirical one into the other. But the way I've described it already indicates maybe that there are some problems with this from a strictly logical point of view. So this quote from Supps, I think, is pretty revealing of the situation. He says, keep in mind, this is at the end of a book about formal logic. So he's just like written an introduction to formal logic, and at the end, this is what he says about his approach to defining set theoretical predicates. He says, we will not give a sharp definition of those. Our objective is to elucidate by examples what is involved in defining such predicates. Moreover, we shall assume that the set theoretical framework within which we operate consists not only of general set theory, but also of the full apparatus of classical mathematics, that is the real numbers, functions of real numbers, derivatives and integrals of such functions, and so on. So he's basically saying that he's going to work in sort of ordinary semi-formal mathematics, and that is to say, like the sort of mathematics that mathematicians write, where it's sort of understood that it should be possible to formalize in principle if one were willing to put in the work, but is generally left in a natural language style. So by doing this, I think you actually lose many of the advantages of working with logic in the first place, which is that, for one thing, an advantage of having a model relative to a logical system is that it always gives you a good notion of, it always gives you a notion of morphism or homomorphism between models. I think this is quite relevant because in my experience, scientists tend to have a very good idea of what the objects in their domain of study are, but not often a very good sense of what the morphisms between those should be, or how to formalize that sort of thing. And then you lose the ability to represent the knowledge in a precise way on a computer to benefit from mechanization or automation like you might find in a proof assistant or other software tools. So somehow I think by going in this direction, you get more practical, but you lose a lot of the benefits that you sought to get in the first place. And there's also just sort of a generally puzzling thing to me about some of the way that people talk about this work, which is that in logic, a model is always a model of some theory. It's not just a thing that exists independently on its own. And so it's to say that one defines a theory by defining its class of models is, on the face of it, kind of a strange thing to be saying as well. So to summarize this, on my reading, the linguistic views have the benefit of at least having a precise proposal of what a reasonably precise proposal of what a theory is supposed to be. I think the models tend to play, unfortunately, kind of a marginal role in a lot of those. And they're also quite impractical to work with using standard logical systems. The model theoretic views are quite unclear about what a theory is supposed to be, but they do recognize the importance of models, and they have a relatively, I think, practical approach that, with the caveat that by working semi-formally, often some of the benefits are lost. So the sort of the thesis of this talk is that by adopting some of the methods that have been developed in category theory and categorical logic for many years now, can help deal with some of the problems that arise in these programs, both some of the philosophical problems and I think also some of the practical problems, and to get closer to having formalized theories and models be something that scientists might actually work with. So, if I'm going to use the word categorical logic pretty broadly, I mean, for me, in the broadest sense, it basically encompasses the idea of functorial semantics, which I'll say more about. So this is best known in the areas of logic and type theory, where it's been studied for many decades now. But I think this idea is also present in a lot of the work being done in the field of applied category theory, which is trying to apply, ideas from category theory to the study of systems as they appear in science and engineering. So here are some of the major sort of tenets of the view that I want to argue for. So first of all, I would really like to get away from the idea that we should be looking for, say, like the one true logic in which it is appropriate to formulate scientific theories. I think that you see this not just in philosophy, but also in some of the practical work in knowledge representation, right? So like in the biomedical world, everyone has converged on this thing called OWL, which is good for some representing some kinds of knowledge, and I think much less good for representing other kinds of things. So there's a real tendency to want to standardize around one thing that will build sort of systems and tools on. But I think that you lose a lot by doing that, and then it's better to try to adopt an approach of having a family of logics that are in some way specialized or tailored to the kinds of models that people are using in different parts of science. And the way that that idea gets cashed out in categorical logic is to think that a logic is defined by some kind of category-like structure. And the idea is that the structure available in that category is in that type of category is telling you what sorts of operations and affordances you have available in your logic. And then a theory is a particular choice of category with that structure. So that's a viewpoint that we'll be getting into a bit more here. And a huge advantage of this approach is the ability to incorporate mathematical background knowledge by separating it and putting it into the semantics. So what we'll see about functorial semantics is that like we don't just have to send our types to sets and our terms to functions. You know, we can interpret our theories in other kinds of categories, and by doing that, we can compartmentalize a lot of the background theory that we need into the semantics and focus in our theory on just what is most essential to the domain at hand. And finally, the third point about this, which I won't really be able to get into much into this talk, but sort of in the big picture here is also the idea that, you know, even if we want to acknowledge that different fields of science should be operating within different logics, we might hope to still at least be able to find some connections between those things. We don't probably want to see everyone is just operating entirely in a vacuum independent from everyone else. And category theory there too provides tools to help at a meta level organize these different logical systems. Okay, so I'm going to start to get into some of this now. So I'm going to use some of the technical jargon in this area. If you're not familiar with it, I'm still hoping that you can, you know, take away from this view this as sort of an advertisement, and that I hope you can take away some of the kind of the key points, which I'll try to highlight as we go. So the field of categorical logic unquestionably begins with Leverre's thesis in 1963 called The Functorial Semantics of Algebraic Theories. And algebraic theories are definitely much more in their typical usage about math than science. They're the sort of theories in which it's appropriate to axiomatize things like groups and rings and monoids and so forth. But I think they're still a good place to start. One, because it's a pretty nice, clean story, and also because it already illustrates in a different context and math rather than science, sort of the viewpoint that I'm taking, which is that, you know, algebraic theories are a type of theory designed to conveniently work with a rather restrictive class of mathematical structures, and it does what it does very well and nothing more. So in that sense, it is itself a sort of specialized logic, just one that's more typically used in math than in science. So we can start to see in this sort of, in some ways, prototypical setting some of the dictionary between logic and type theory on the one hand and category theory on the other. So the basic viewpoint here is that an algebraic theory should be identified with a small category that has finite products, where the types in the theory, or the sorts, correspond to objects in the category, and the operations or terms that are available in the theory correspond to morphisms in the category. And with that identification, a model of the theory is a functor from the category into set that preserves the structure available. So in this case, it preserves products. And then finally, a model homomorphism is a natural transformation. So for me, like the original insight of this whole sort of story was noticing that the concept of a natural transformation, which was invented for different reasons, is precisely the notion of model homomorphism in this context. So to give a sense of, so I wanted to illustrate now via some examples, some aspects of this way of doing things. So the first thing we'll see are 3 different styles in which we can describe some famous algebraic theories, namely the theory of monoids and the theory of groups. So this first one is in the style of what's sometimes called a sketch, and I'm starting with it because it sort of looks most directly category theoretic, right? We give ourselves some objects and some arrows, and then specify some equations that should be satisfied via commuting diagrams. So this is sort of one form of a diagrammatic specification. So I won't dwell on these in detail, but you know, so like in the first theory, we're getting the multiplication operation and the unit, and then these sets of diagrams are associativity and unitality. And then in the theory of groups, we had another morphism, which is the inverse operation, and then we get 2 laws saying that it does indeed provide an inverse for the multiplication. So here's another way to present the same theories, now using a different syntax. So this is a type theoretic kind of syntax. This is what might be called algebraic type theory. This may look much more familiar to you. This is much closer to how one would describe algebraic theories in a traditional syntactic presentation. And then something that may look quite wild is we can use yet another syntax if we like, which is based on the concept of a string diagram or a wiring diagram, where we now view morphisms as being described by these figures, and where which we're reading from top to bottom. And so like this circle has 2 inputs and 1 output, that's the multiplication, and this one has no inputs and an output, that's the unit. And then by composing these together according to certain rules, we can write down the axioms yet again. And so here briefly is the theory of groups presented in the same style. So so I'm not going to dwell on that too much, but the main point that I wanted to illustrate by showing this 3 different ways of dealing with syntax is to show how the categorical approach to logic helps overcome some of the concerns about the extent to which theories are linguistic or extra linguistic, which I noted have sort of plagued a lot of the discussion in the philosophy of science literature. So the answer from the point of view of categorical logic is that theories are both syntactic and also in a sense not syntactic, right? So on the one hand, we present theories in a syntactic way, and there are a variety of means to do that. Certainly in the case of algebraic theories, there's at least 3 ways of doing it, and I've shown them. And the point is that all 3 of those can be made sort of perfectly rigorous if you want to. Even the diagrammatic one can be made perfectly rigorous with some effort. But the theory itself is an algebraic structure. So these are presentations that generate a category with finite products, and that category, which is the theory, is in some sense invariant to the differences in both the system in which you use to give the presentation, as well as to certain different choices in axiomatization. So I presented the same axioms here, but there are lots of ways to axiomatize a group equationally, and they lead to the same algebraic theory. So I think this is the first sort of powerful insight from categorical logic, right? Is that when it comes to this question of being linguistic or not, we get to have our cake and eat it too. So this story about algebraic theories and categories with finite products was the beginning of a big research program that went on for many years, and some ways is still going on. So in this figure, I'm illustrating some of the other kinds of theories that people have considered, and the types of categorical structures that they correspond to. So another very famous one is the correspondence between lambda calculus with product types and Cartesian closed categories. So this is a beautiful story. I'm not going to talk about this picture too much more, because most of this stuff to me is geared towards logic as it's used for mathematics, and I want to be talking now, finally getting to the main thrust of the talk, using techniques similar in spirit for the sciences. So the idea is here to use some of the same conceptual apparatus of categorical logic, but probably to use different notions of logic and different kinds of semantics for different sorts of areas. So within the field of applied category theory, and other fields as well, people have explored different parts of this network of logic. So again, I've got algebraic theories in the middle, but people have used other types of categories equipped with monoidal products, which are a product-like structure, to study other sorts of things. And the example that I'll be honing in on are the use of Markov categories as a synthetic way to reason about probability and statistics. So the idea, so we're going to start with what will be our semantics, right? So getting back to this point, so we want to interpret these theories not just in ordinary sets and functions, but we want to interpret them in a place where the morphisms are some kind of randomized functions and or stochastic functions, and the precise term that people use for that is a Markov kernel or a stochastic kernel. So these are functions that are valued in probability distributions. And so there's a category of where whose objects are let's say measurable spaces, and whose morphisms are these stochastic kernels between them. This category is often called Stoke. So the and then in recent years, although it has a long sort of prehistory, there's been a push to axiomatize some of the essential features of this category in a purely sort of categorical way. So without reference to the analytic features of probability distributions and measures and so forth. And one of the main approaches that has emerged is what's called a Markov category. So and some of the words here may well make no sense to you, but the basic idea is that it's a type of category that's equipped with a monoidal product. So this product is supposed to capture a stochastic phenomenon, so it's not going to satisfy the usual universal property of like a Cartesian product, but we can still axiomatize the product-like aspect of it, as well as being equipped with operations for copying and deleting data. So I'll give a little indication of kind of what this axiomatization is about. So the it turns out that even with this quite minimal definition, a surprising amount of of probability theory can be reproduced in a synthetic or axiomatic style within Markov categories. So Tobias Fritz and his collaborators have been working on this for some years now and have shown lots of interesting results about different kinds of theorems and probability. But here we're going to start with like the beginning of this whole story, which is just that Markov categories, kind of the first and most simplest thing you can do with them is distinguish between deterministic and non-deterministic morphisms. So it turns out that at least if you have some regularity conditions on your measures, then a Markov kernel between measurable spaces is deterministic. In other words, it is the image of a regular old function, if and only if it commutes with copying. That is to say that if you apply your Markov kernel and then copy the output, that is the same in distribution as taking your input and copying it and then applying your Markov kernel to each of those copies. That insight becomes the axiomatic basis for a morphism being deterministic in a Markov category. So this characterization is taken as the definition of what it means for a morphism in a Markov category to be deterministic. So that's one thing, simple thing you can do in a Markov category. You can do other things. And so the idea then is to say, well, okay, we are going to try to follow more or less. There's one interesting departure, the pattern of categorical logic. So we'll define a statistical theory to be a small Markov category, and I'm also giving it some extra structure, like the ability to specify different kinds of linear algebraic structure, which I haven't described here. So that's analogous to, in the case of algebraic theories, having a category with finite products. And then there's sort of a new ingredient here, which is that for statistics, there's a distinguished morphism that is picked out, which is supposed to represent the sampling distribution. And so then we can say that a model of a statistical theory is a functor from this category T representing the theory into Stoke, this category of measurable spaces in Markov kernels. And it's not just any old functor; it needs to preserve the structure that's present in a Markov category. And then finally, a model homomorphism is again a kind of natural transformation. In this case, a monoidal natural transformation. And so the slogan of this approach is that a statistical model is a model of a statistical theory, which sounds like a tautology, but it's not in the typical way of doing things. So in statistics, going back to the early 20th century, there is a notion of statistical model, but it doesn't have around it much of a formal axiomatic. It's just directly postulated in terms of the content of probability theory. And what this is saying is that, we can recover that notion of model, but we can also have a part of the description of the model that is within a formal language. So to give a little bit of an example of kind of what this might look like, so every statistician's favorite model, linear model. So this is one of the kind of theory that you could present in this. So here I'm going to present it in using the graphical sort of approach that I illustrated earlier. So in this model, you give yourself some different objects. Some of them are equipped with a vector space structure and others with a different kind of structure, the structure of a conical space, the idea being that the variance parameter is somehow constrained to be non-negative or more generally positive, semi-definite. You can pick out some deterministic linear maps, which are basically giving you the design matrix. And then you pick out another component, which is giving you the stochastic piece of the model. So it turns out, sort of interestingly, that you can completely axiomatize in algebraic terms the equations that will ensure that actually this any model of this theory interpreted in Stoke has to give you a Gaussian sampling distribution, which is the standard sampling distribution for a linear model. And then finally, the sampling morphism is specified by this string diagram here, which is basically saying you take your parameters in, you copy them out, you apply your design matrices, and then finally you apply the noise piece of the model. So this separates out some of, in statisticians' mind, there's always an idea that there's a deterministic component of the model, there's an error part. And what this apparatus of statistical theories does is let you separate all those out and sort of describe those in a fully in a precise synthetic language. So okay, so right, so what are some of the lessons from this? So picking up on some points that I've made previously in the talk. So statistical theories let you capture at least certain aspects of statistical models in a synthetic style, so they can distinguish between determinism and non-determinism, for example, or linearity versus non-linearity, which are both common distinctions that statisticians care about. We capture the background mathematics by looking at functorial semantics in this category Stoke. So we don't need to be in the business of giving from first principles axiomatic account for probability and measure theory. You put that in the semantics. And finally, you get for free from this notion of morphism between statistical models, which surprisingly turns out to be a pretty novel concept. I mean, statisticians have not traditionally had a very clear notion of what that is, even if in certain applications, like in the study of invariance and equivariance, they really could have used one. So I'll just note here. So I focused in this talk on sort of one use case that I've personally worked on and been interested in, which are statistical theories and models. I just want to indicate that things similar to this paradigm have been carried out in other areas. So really, one of the most developed applications, I would say, actually, is in quantum mechanics, where people have specifically quantum mechanics as intended for quantum computation, where people have axiomatized using similar in spirit sort of structures based on monodal categories to capture the category of finite dimensional Hilbert spaces. And this is now a pretty well-developed area. And even though people in this area are less likely to talk about it in such overtly logical terms as I have, I think it actually fits quite well into the sort of picture that I'm telling here. So just that's a pointer for another thing to look at if you're so inclined. Okay, so to conclude, in this talk, I've outlined a categorical approach to formalizing scientific theories and models, and I've illustrated it at least in the case of statistical models. I've gestured at another application, so I think it's a promising direction. There's definitely very significant work that remains to continue to sort of to try to unify more things within this general approach, as well as to operationalize it through practical tools that scientists and engineers can use. And then the last part of this talk, I'll very briefly describe some efforts along both of those lines. So a lot of the work, as I said at the beginning of this talk, a lot of the work in the field of applied category theory, I think, can be seen as involving functorial semantics in the broadest sense. So, for example, one area that I've worked some in is in the use of compartmental models, ODE-based models in epidemiology, where one can use a graphical language like Petri nets or stock flow diagrams as as something like a theory, and then have a functorial interpretation of those in a suitable category of ODEs or dynamical systems. And in fact, with a number of colleagues and collaborators. We've implemented a fair amount of this stuff in software. You can actually use it. It doesn't always exactly follow the standard schema of categorical logic that I've outlined here. So it suggests to me that there's more thinking to be sure to be done about how to see these things in a hopefully unified light. And on the topic of unity, so this is my last kind of point here. So another very often discussed question in the philosophy of science is whether and to what extent there's any unity in science, like between different fields. Are all the fields just doing their own thing, or is there some overarching sense of method? So the viewpoint that I've arrived at, and I think the one that's sort of implicit in this talk, is that theorizing and modeling, and as it happens in science, I think is very much should be seen as pluralistic and varied. And I've explicitly advocated for an approach to using logic in science that recognizes that variety. But we also do want to see, if we can, at least some connections between those different things. And so, as I indicated earlier, I think that category theory can help as a further organizing principle to connect different categorical logical systems together. This is something that I'm working on a lot right now. Actually, I'm pretty excited about. I won't get into it, but just to say that I think there's just lots of really interesting things to be thinking about here. And I think a lot of these mathematical tools, many of them have been around for a long time, and they're known to specialists, but they haven't really percolated as much as I would hope, even within mathematics itself, let alone outside of it. So I'm hoping to see these ideas gradually start to make more of an impact in the sciences. So thanks a lot for your attention. I know we're coming up against lunch, so thanks for